The Internet Protocol Introduction. IP is the workhorse protocol of the TCP/IP protocol suite. All TCP, UDP, ICMP, and IGMP data gets transmitted as IP datagrams. IP provides a best effort, connectionless datagram delivery service. By best effort, we mean there are no guarantees that an IP datagram gets to its destination successfully. Although IP does not simply draft all traffic unnecessarily, it provides no guarantees as to the fate of the packets it attempts to deliver. When something goes wrong, such as router temporarily running out of buffers, IP has a simple error handling algorithm. Throw away some data, usually the last datagram that arrived. Any required reliability must be provided by the upper layers, TCP. IPv4 and IPv6 both use this basic best effort delivery model. The term connectionless means that IP does not maintain any connection state information about related datagrams within the network elements, like within the routes. Each datagram is handled independently others, from all other others. This is also mean that IP datagrams can be delivered out of order. If a source sends two consecutive datagrams, first A then B, to the same destination, each is routed independently and can take different paths, and B may arrive before A. Other things can happen to IP datagrams as well. They may be duplicated in transit, and they may have their data altered as the result of errors. Again, some protocol above IP, usually TCP, has to handle all of these potential problems in order to provide an error-free delivery abstraction for applications. In this chapter, we take a look at the fields of the IPv4, see Figure 5.1, and IPv6, see Figure 5.2 headers, and describe how IP forwarding works. The official specification for IPv4 is given in RFC 0791. A series of RFCs describe IPv6 starting with RFC 2460. Figure 5.1, the IPv4 datagram. The header is of variable size, limited to 15 32-bit words, 60 bytes by the 4-bit IHL field. A typical IPv4 header contains 20 bytes, no options. The source and destination address are 32 bits long. Most of the second 32-bit word is used for the IPv4 fragmentation function. A header checksum helps ensure that the fields in the header are delivered correctly to the proper destination but does not protect the data. Figure 5.2. The IPv6 header is of fixed size, 40 bytes, and contains 128-bit source and destination addresses. The next header field is used to indicate the presence and types of additional extension headers that follow the IPv6 header, forming a daisy chain of header that may include special extensions or processing directives. Application data follows the header chain, usually immediately following a transport layer header. IPv4 and IPv6 headers. Figure 5.1 shows the format of an IPv4 datagram. The normal size of the IPv4 header is 20 bytes, unless options are present, which is rare. The IPv6 header is twice as large but never has any options. It may have extension headers, which provide similar capabilities as we shall see later. In our pictures of headers and datagrams, the most significant bit is numbered 0 at the left, and the least significant bit of a 32-bit value is numbered 31 on the right. The 4 bytes in a 32-bit value are transmitted in the following order: bits 0 to 7 first, then bits 8 to 15, then 16 to 23, and bits 24 to 31 last. This is called big endian byte ordering, which is the byte ordering required for all binary integers in the TCP or IP headers as they traverse a network. It is also called a network byte order. Computer CPUs that store binary integers in other formats, such as the little endian format used by most PCs, must convert the header values into the network byte order for transmission and back again for reception. IP header fields. The first field, only 4 bits or 1 nibble wide, is the version field. It contains the version number of the IP datagram, 4 for IPv4 and 6 for IPv6. The headers for both IPv4 and IPv6 share the location of the version field but no others. Thus, the two protocols are not directly interoperable. A host or router must handle either IPv4 or IPv6 or both, called dual stack separately. Although other versions of IP have been proposed and developed, only versions 4 and 6 have any significant amount of use. The IANA keeps an official registry of these version numbers. For the Internet Header Link IHL field is the number of 32-bit words in the IPv4 header, including any options. Because this is also a 4-bit field, the IPv4 header is limited to a maximum of 15 32-bit words or 60 bytes. Later, we shall see how this limitation makes some of the options, such as the record route option, nearly useless today. The normal value of this field when no options are present is 5. There is no such field in IPv6 because the header length is fixed at 40 bytes. Following the header length, the original specification of IPv4 RFC 0791 specified a type of service, TOS byte, and IPv6 RFC 2460 specified the equivalent traffic class byte. Use of this never became widespread, so eventually this 8-bit field was split into two smaller parts and redefined by a set of RFCs: RFC 3260, RFC 3168, RFC 2474, and others. The first 6 bits are now called the differentiated services field, DS field, and the last 2 bits are explicit congestion notification, ECN field, or indicator bits. These RFCs now apply to both IPv4 and IPv6. These fields are used for special processing of datagram when it is forwarded. We discussed them in more detail in section 5.2.3. The total length field is the total length of the IPv4 datagram in bytes. Using this field in the IHL field, we know where the data portion of the datagram starts and its length. Because this is a 16-bit field, the maximum size of an IPv4 datagram, including header, is 65,535 bytes. The total length field is required in the header because some lower layer protocols that carry IPv4 datagrams do not accurately convey the size of encapsulated datagrams on their own. Ethernet, for example, pads small frames to a minimum length of 64 bytes. Even though the minimum Ethernet payload size is 46 bytes, see Chapter 3, an IPv4 datagram can be smaller as few as 20 bytes. If the total length field were not provided, the IPv4 implementation would not know how much a 46-byte Ethernet frame was really an IP datagram, as opposed to padding, leading to possible confusion. Although it is possible to send a 65,535 byte IP datagram, most link layers such as Ethernet are not able to carry one this large without fragmenting it, chopping it up into smaller pieces. Furthermore, a host is not required to be able to receive an IPv4 datagram larger than 576 bytes. In IPv6, a host must be able to process a datagram at least as large as the MTU of the link to which it is attached, and the minimum link MTU is 1 to 80 bytes. Many applications that use the UDP protocol, see Chapter 10, for data transport like DNS or DHCP, etc., use a limited data size of 512 bytes to avoid the 576 byte IPv4 limit. TCP chooses its own datagram size based on additional information, see Chapter 15. When an IPv4 datagram is fragmented into multiple smaller fragments, each of which itself is an independent IP datagram, the total length field reflects the length of the particular fragment. Fragmentation is described in detail along with UDP in Chapter 10. In IPv6, fragmentation is not supported by the header, and the length is instead given by the payload length field. The field measures the length of the IPv6 datagram, not including the length of the header. Extension headers, however, are included in the payload length field. As with IPv4, the 16-bit size of the field limits its maximum value to 65,535. With IPv6, however, it is the payload length that is limited to 64 kilobytes, not the entire datagram. In addition, IPv6 supports a jumbogram option, see section 5.3.1.2, that provides for the possibility, at least theoretically, of a single packet with payload as large as 4 gig, 4,294,967,295 bytes. The identification field helps identify each datagram sent by an IPv4 host. To ensure that fragments of one datagram are not confused with those of another, the sending host normally increments an internal counter by 1 each time a datagram is sent from one of its IP addresses and copies the value of the counter into the IPv4 identification field. This field is most important for implementing fragmentation, so we explore it further in Chapter 10, where we also discuss the flags and fragment offset fields. In IPv6, this field shows up in the fragmentation extension header, as we discussed in section 5.3.3. The time to leave field, or TTL, sets an upper limit on the number of routers through which a datagram can pass. It is initialized by the sender to some value, 64 is recommended, RFC 1122, although 128 or 255 is not uncommon, and decremented by 1 by every router that forwards the datagram. When this field reaches 0, the datagram is thrown away, and the sender is notified with an ICMP message, see Chapter 8. This prevents packet from getting caught in the network forever should an unwanted routing loop occur. Note, the TTL field was originally specified to be maximum lifetime of an IP datagram in seconds, but routers were also always required to decrement the value by at least 1. Because virtually no routers today hold on to a datagram longer than 1 second under normal operation, the earlier rule is now ignored or forgotten, and in IPv6, the field has been remained to its de facto use, hop limit. The protocol field in the IPv4 header contains a number indicating the type of data found in the payload portion of the datagram. The most common values are 17 for UDP and 6 for TCP. This provides a demultiplexing feature so that the IP protocol can be used to carry payloads of more than one protocol type. Although this field originally specified the transport layer protocol, the datagram is encapsulating. It is now understood to identify the encapsulated protocol, which may or not be a transport protocol. For example, other encapsulation are possible, such as IPv4 and IPv4, value 4. The official list of the possible values of the protocol field is given in the assigned number page AN. The next header field in the IPv6 header generalizes the protocol field from the IPv4. It is used to indicate the type of header following the IPv6 header. This field may contain any values defined for the IPv4 protocol or any of the values associated with the IPv6 extension headers described in section 5.3. The header checksum field is calculated over the IPv4 header only. This is important to understand because it means that the payload of the IPv4 datagram, like TCP or UDP data, is not checked for correctness by the IP protocol. To help ensure that the payload portion of an IP datagram has been correctly delivered, other protocols must cover any important data that follows the header with their own data integrity checking mechanisms. We shall see that almost all protocols encapsulated in IP, ICMP, IGMP, UDP, and TCP have a checksum in their own headers to cover their header and data, and also to cover certain ports of the IP header they deem important, a form of layering violation. Perhaps surprisingly, the IPv6 header does not have any checksum field. Note, omitting the checksum field from the IPv6 header was a somewhat controversial decision. The reasoning behind this action is roughly as follows. Higher layer protocols requiring correctness in the IP header are required to compute their own checksums over the data they believe to be important. A consequence of errors in the IP header is that the data is delivered to the wrong destination is indicated to have come from the wrong source, or is otherwise mangled during delivery. Because bit errors are relatively rare, thanks to fiber optic delivery of internet traffic and stronger mechanisms are available to ensure correctness of the other fields, higher layer checksums or other checks, it was decided to eliminate the field from the IPv6 header. The algorithm used in computing a checksum is also used by most of the other internet-related protocols that use checksum and is sometimes known as the internet checksum. Note that when an IPv4 datagram passes through a router, its header checksum must change as a result of decrementing the TTL field. We discussed the methods for computing the checksum in more detail in section 5.2.2. Every IP datagram contains the source IP address of the sender of the datagram and the destination IP address of where the datagram is destined. These are 32 bits values for IPv4 and 128-bit values for IPv6, and they usually identify a single interface on a computer. Although a multicast and broadcast addresses, see Chapter 2, violate this rule. While a 32-bit address can accommodate a seemingly large number of internet entities, 4.5 billion, there is widespread agreement that this number is inadequate, a primary motivation for moving to IPv6. The 128-bit address of IPv6 can accommodate a huge number of internet entities, as was restated in IPv6 in H05. IPv6 has 3.4 times 10 raised to 38, 340 undecillion addresses. Quoting from H05 and others, the optimistic estimate would allow for 3 something something addresses per square meter of the surface of the planet Earth. It certainly seems as if this should last a very, very long time indeed. The Internet Checksum. The Internet checksum is a 16-bit mathematical sum used to determine with reasonable high probability whether a received message of or portion of message matches as the one sent. Note the Internet checksum algorithm is not the same as the common cyclic redundancy check, which offers stronger protection. To compute the IPv4 header checksum for an outgoing datagram, The value of the datagram's checksum field is first set to 0. Then the 16-bit ones complement sum of the header is calculated. The entire header is considered a sequence of the 16-bit words. The 16-bit ones complement of the sum is then stored in the checksum field to make the datagram ready for transmission. Ones complement addition can be implemented by end-round carry addition when a carry bit is produced using conventional 2 complement addition. The carry is added back in as a 1 value. Figure 5.3 presents an example where the message contents are represented in a hexadecimal. When an IPv4 datagram is received, a checksum is computed across the whole header, including the value of the checksum field itself. Assuming there are no errors, the computed checksum value is always 0, a ones complement of the value FFFF. Note that for any non-trivial packet or header, the value of the checksum field in the packet can never be FFFF. If it were, the sum prior to the final ones complement operation at the sender would have to have been 0. No sum can ever be 0 using ones complement addition unless all the bytes are 0, something that never happens with legitimate IPv4 header. When the header is found to be bad, the compound checksum is non-zero. The IPv4 implementation discards the received datagram. No error message is generated. It's up to the higher layers to somewhat detect missing datagram and retransmit if necessary. Figure 5.3. The internet checksum is the ones complement of a ones complement 16-bit sum of data being checksum. 0 padding is used if the number of bytes being summed is odd. If data being summed includes a checksum field, the field is first set to 0 prior to the checksum operation and then filled in with compound checksum. To check whether an incoming block of data that contains a checksum field, header, payload, etc. is valid, the same type of checksum is computed over the whole block, including the checksum field. Because the checksum field is essentially the inverse of the checksum of the rest of the data, computing the checksum can correctly receive data should produce a value of 0. What problem does your system aim to solve? Our system addresses two major gaps in current telehealth communication tools. First, most platforms remain basic messenger-style applications with no built-in intelligence. Second, attempts to add AI often risk data exposure or privacy non-compliance. SecureChat AI Web bridges this gap by integrating AI summarization triggered via server-side webhooks that store summaries in Firestore while maintaining strong access control and compliance with the Philippine Data Privacy Act, RA 10173. Why did you choose the title SecureChat AI Web? SecureChat highlights our privacy-first communication focus, while AI Web emphasizes that the platform operates through a secure web interface enhanced by AI automation. The name reflects our goal of blending real-time teleconsultation and data privacy with AI summarization, all within a single secure web environment. What motivated your group to pursue this topic? During the pandemic, healthcare relied heavily on unstructured messaging apps, lacking privacy and intelligence. We saw a need for a Philippine-compliant, AI-enhanced system that supports real-time consultation while respecting confidentiality and access control requirements. What makes your system unique compared to existing telehealth platforms? Other apps still rely on direct chat or call features without AI. Secure Chat AI Web automates summary generation of live kit sessions via webhook-triggered OpenAI API calls, storing results securely in Firestore. It also introduces invite-based gated access using signed, time-limited JW links, preventing public access to sessions and transcripts. Who are your intended users and beneficiaries? Our main users are doctors and patients who need secure, log, and AI-supported consultation records. Doctors gain time-saving summaries. Patients gain private access without exposing conversation through generic chat apps. Hospitals and clinics benefit from compliant, audit-friendly architecture. Can you describe your system architecture and how each module interacts? Our system follows a server-driven modular design. Front end, Next.js plus custom CSS plus LiveKit components for the user interface and real-time sessions. Backend API routes handle JWT invite validation, AI summarization request, and rate limiting. LiveKit webhooks trigger AI summarization after sessions. OpenAI API processes summaries server-side, which are then stored in Firestore. All communication is secured through signed tokens and HMAC verified webhooks. How does your system ensure that only authorized patients can access consultation sessions? Access is managed through signed, time-limited invite links generated by the doctor. Each link can include optional constraints, country, IP, browser, or first-use device binding. Once used or expired, the invite becomes invalid, ensuring only intended recipients can join. Why did you choose Next.js for the front end? Next.js provides a React-based framework ideal for full-stack web applications. Its API routes simplify back-end integration for token generation and AI calls. The combination allows real-time UI updates with a clean, custom CSS interface integrated with LiveKit components. What database and backend technologies did you use and why? We use Firebase Firestore for structured data storage and Firebase authentication for account management. Firestore provides fast read or write performance and integrates seamlessly with serverless API routes. It stores chat logs, summaries, and invite metadata securely. How did you ensure your system is user friendly? We designed the interface around LiveKit's modern UI components and clean, readable layout using custom CSS. We prioritize accessibility through large buttons, clear labels, and real-time session feedback indicators. How does your AI summarization feature work? After a LiveKit session ends, a webhook event triggers a backend API route. The API compiles relevant conversation text, sends it to the OpenAPI model, and stores the resulting summary in Firestore. The process is automated, secure, and asynchronous to prevent UI blocking. Why is your AI summarization implemented server-side instead of client-side? Client-side AI models can securely manage API keys and are limited by browser resources. By performing summarization on the server, we keep credentials secure, apply rate limiting, and maintain consistent processing. The backend is protected through HMAC verified webhooks and signed API routes. What are the limitations of your AI summarization module? Summaries rely on the quality of input transcripts. Since summarization runs post-session, user must wait briefly before seeing results. Also, model accurately depends on the text clarity and may omit contextual nuances. How does your system comply with Philippine Data Privacy Act? We implement transparency. Users are informed before data use. Legitimate purpose. AI summaries are for authorized consultation only. Security. All access uses signed JWT tokens and verified webhooks. Data minimization. Only essential conversation metadata is stored. Raw video or audio are not retained. All this align with RA 10173 compliance principles. What encryption or security measures protect user data? We use transport layer security for all communications, HS 256 signed JWTs for access tokens, and HMAC verification for webhook requests from LiveKit. Additionally, we implement per IP rate limiting and input sanitation to mitigate abuse.